planet Earth revolves endlessly in space. Man, searching for knowledge, directs his studies increasingly toward the space around the Earth, toward the solar system and the universe. He uses sensitive radio instruments to listen to faint signals coming from distant sources in the universe. He uses delicate optical instruments to study the sun. Yet with all this reach into space, one of the most difficult research problems encountered by scientists is the study and measurement of the upper atmosphere surrounding the Earth. The problem begins at a height of 300 kilometers, about 185 miles, in the region called the ionosphere, and extends to great heights approaching interplanetary space. Here, we see how the ionosphere can reflect radio waves. This characteristic helps long-distance communications, but it hinders the use of radio techniques to study atmospheric constituents above the ionosphere. Rockets and satellites help significantly. Satellites can detect and measure constituents of the outer atmosphere and even the exosphere, as the region beyond is called. Explorer 1 and Pioneer 3 discovered the Van Allen radiation belts. This is an artist's conception of the Van Allen belts. These vast regions above the Earth's ionosphere are composed of trapped electrons and protons. It is true that observations made by satellites have permitted scientists to cross a new threshold into space research. But orbiting satellites and expensive specialized rockets can provide only snapshot observations of the ionosphere. They cannot give us details for a specific geographic location. Continuous observations above the ionosphere for a fixed location are needed. This film is the story of how scientists of the National Bureau of Standards, U.S. Department of Commerce, tackled the problem and developed a new research technique using scatter radar for space research from the ground. It is the story of a search for a location, of building an observatory and an entire research facility. And lastly, it is a heartening story of international cooperation on a person-to-person basis. Let's look at the ionosphere again to understand the problem better. The ionosphere is composed of neutral constituents, ionized constituents, and free electrons. It is the radio properties of the regions of free electrons that permit long-distance radio communication in the so-called shortwave bands. Up to frequencies of about 30 megacycles per second, free electrons reflect radio frequency energy back toward the Earth. But at frequencies above about 30 megacycles per second, the radio waves penetrate the ionosphere. For years, scientists have used the ionoson, such as this model C4, to measure electron density variations. But its use is limited to the denser regions of the atmosphere, such as the F layer at 300 kilometers. Here, there may be up to several thousand electrons per cubic millimeter, or millions per cubic centimeter. But beyond this range, the density of free electrons decreases. Scientists wanted to know how far above the F layer free electrons extended. The problem was to devise a way to measure them. Here we see two atoms of oxygen. An electron detaches from one of them. When detached, it is a free electron and can respond to electric forces imposed upon it. When a radio wave passes by, the electron oscillates with the wave and re-radiates or scatters its energy incoherently in all directions. The problem is to excite these electrons sufficiently so that they will re-radiate enough energy to be detected from the ground. What is needed is an exceptionally powerful transmitter, an extremely large antenna, and a very sensitive receiver. Here are the Boulder, Colorado laboratories of the National Bureau of Standards. One of these, the Central Radio Propagation Laboratory, conducts basic research in the Earth's ionosphere and upper atmosphere and in space. To Dr. Kenneth Bowles, a physicist with the Boulder Laboratories, goes the credit for solving the problem. Here he confers with a colleague. Acting on a suggestion by Dr. W.E. Gordon of Cornell University, Dr. Bowles employed a technique using the incoherent scatter of radio waves by electrons in the ionosphere. This transmits a powerful pulsed radio signal in a narrow beam. The beam penetrates the ionosphere and excites free electrons in the area above. They scatter a weak signal. The extremely sensitive antenna, now acting as a receiver, detects the faint scattered signal which comes back to Earth. The system can detect faint echoes from electron densities as low as 100 per cubic centimeter, such as exist well above the F layer of the ionosphere. Under Dr. Bowles' scientific leadership, the new technique using scatter radar was successfully demonstrated at a field site in 1959. Here, near Havana, Illinois, is a portion of the original antenna used in that pioneer experiment. A breakthrough of great importance had been achieved, promising to make upper atmosphere and space research possible from the ground. The Bureau gave full support to plans to exploit the technique. First, a site was needed where the fullest range of observations and measurements could be made, including studies of the chemical composition of the upper atmosphere. They would be of greatest interest if made near the magnetic equator, where the lines of force of the Earth's magnetic field are nearly horizontal, giving the electron unusual characteristics. The pulsed radar signals could then travel perpendicularly to these lines of force and excite free electrons. This would allow us to observe the gyrations of those excited electrons, determine the characteristic frequency of the ions controlling these movements, and identify the chemical composition of atmospheric gases. Certain of the gases, such as nitrogen and oxygen, dominate in lower regions. At greater heights, regions of oxygen, helium, and hydrogen dominate. With scatter radar, we can learn the heights of these various regions of gases and study the total composition of the atmosphere. Where could an ideal site be found? It should be on the magnetic equator, but as close as possible to the United States to shorten travel and shipping time. These requirements narrowed the choice to South America, and we decided to examine Lima, Peru. Especially important in our consideration was a year-round temperate climate such as found here. Lima, the capital of Peru, is an ancient city, rich in tradition.